Hi everyone, welcome to our lesson on impulse. This lesson will follow on many of the concepts introduced in the momentum video. So if you haven't seen the momentum video, go and watch that video so you understand what's going on early in this lecture. Now, impulse. We said in the momentum lesson, the total momentum of the system doesn't change. So delta P system equals 0. There is no change in the momentum of the system, which enables us to work out if two blocks are traveling at different speeds and then lock up, we should be able to work out what speed they're traveling at. But of course, common sense tells us that the momentum of individual objects is changing. So impulse, given by the symbol I, is equal to delta P, the change in momentum of the object, but not the system. And it's also equal to force multiplied by time. So to actually change the momentum of an object, you need to apply a force and you need to apply it for a certain time. If you don't apply a force, of course you're not going to change an object. And if you don't apply it for any time, well, there's no time for the object to actually change momentum. So let's look at how impulse ties in to the concepts we already understand about momentum. This question I have down here should be familiar to most because we did it last lesson. A block moving at 5 meters a second, weighing 10 kilograms, collides with a block moving at negative 10 meters a second, so that's in this direction, and that second block weighs 2 kilograms. Then they lock up. Let's figure out the velocity of these blocks locked together. So the momentum in this system is equal to the sum of all the individual momenti. So that can also be written as the sum of the individual momenti. The momentum of this block is equal to 10 times v, 10 times 5. So 10 times 5 plus the momentum of this block, which is 2 times negative 10. And that equals 50. Take away 20, equaling 30. And of course the unit is kilograms times meters per second. Since the momentum of the system is concerned, delta P system equals 0, we know that the momentum in this particular state also has to be 30 kilograms times meters per second. So we start off with that assumption. P equals 30 kilograms times meters per second, and that must equal the mass of this block, which is 12, multiplied by its velocity, so that equals mv, and that is equal to 12v. Therefore, v equals 30 on 12 equals 2.5 meters per second. Since we got a positive answer, the block is moving in this direction. Now let's talk about impulse. I'll move this down. So when we're talking about impulse, we have to specify which object we're talking about. Let's talk about this block here. So it exists here alone, and here it's connected, but we're still going to think of it as a block alone. I said impulse was equal to the delta P of the object. The momentum of the object here, we said was equal to negative 20. Let's figure out what it is here. P equals mv, and that equals 2, thinking of it in isolation, multiplied by 2.5, which equals 5. Therefore, delta P equals P final take P initial, which equals 5 take away negative 20, which equals 25 impulse. And the units for impulse, I should have said this before, is in newtons seconds. So force is newtons, time is seconds, so as you can see the units follow the formula. It's newton seconds, that's 25 newton seconds. Now let's look at the impulse on this block here, because it'll show us something interesting about impulses and Newton's, Newton's third law. The momentum for this block we said was 50 kilograms times meters per second, and over here the momentum of the 10 kilogram block is equal to mv, which is equal to 10 times 2.5, which is equal to 25 kilograms meters per second. So delta P, we'll make sure we know up here, this is the 2 kilogram and this is the 10 kilogram. Delta P equals PF, take P initial, and that PF equals 25, P initial equals 50, that's negative 25 Newton seconds. So the impulse applied by block 10 to block mass 2 is 25 Newton seconds, and the impulse applied to block 10, which was actually by block 2, when they collided, block 2 applied a force to block 10, is equal to the negative 25. This conserves the momentum in the system. Now we haven't really we've talked a lot about this here, just the delta P. In the next example we'll talk about the force times time and see how that comes into it. Okay, here's an example a lot of people are familiar with. We have a golf ball and then it's struck into the air and it's moving at velocity 80 meters per second. And of course here it's sitting on the ground, velocity is 0, and the mass of the golf ball, I looked it up, it's about 45 times 10 to the negative 3 kilograms, 45 grams, and it's the same in the second snapshot. 45 times 10 to the negative 3 kilograms. Let's figure out delta P. Delta P is equal to the final take away the initial, and that's equal to, well, the final is equal to 45 times 10 neg 3 m times velocity times 80, and the initial, since v is 0, the initial momentum is 0. So this is equal to, what have I got here? 3.6 kilograms meters per second. If this is the delta P, we know that that must also be the impulse applied to the golf ball by whatever club swung down and connected with it. So this is also equal to the impulse, which we know is equal to force times time. And sorry, I've got this unit wrong. Delta P, since I'm talking about impulse, is in newtons seconds. And since this is in force times time, here's the tricky part that's different to momentum. If I say the time for this collision was 0.0005 seconds, I'm saying that the time in which the impulse was applied was 0.005 seconds. This is the time in which the club was theoretically in contact with the ball. Then I can say that the impulse, I, which was equal to 3.6, was equal to force multiplied by time, which is in this case 0.0005. So to find the average force applied to that golf ball, I take 3.6 and divide it by 0.0005, giving 7,200, and the unit here of course is newtons. And interestingly, 3.6 was in newtons seconds, the impulse, and time is in seconds, so newtons seconds divided by seconds is just newtons. In that way, the units give you a clue as to whether you got the formula right. So impulses, if they give you the average, if they give you the time it took for that impulse to be applied, you can figure out the average force. If they gave you the average force, you could also figure out the time in which that impulse was applied. Let's look at a real-world example of impulses. This is the Space Shuttle. Merging with the ISS, the International Space Station. And the mass of the shuttle is 78 tons. That's 78 times 10 to the 3 kilograms. And the mass of the ISS, so I'll say shuttle, ISS, the mass of the ISS is 450 times 10 to the 3 kilograms. Now the ISS, we'll say it started out with a velocity of 0. Whoops, I'm going to run out of space. I'll move everything over. And the velocity of the shuttle initially was 10 meters per second. When these two objects collide, of course the people in the shuttle want to get onto the ISS, so they lock together. So we can sketch what we see next. That is the shuttle and the ISS locked together with a combined mass of 450 times 10 to the 3 plus 78 times 10 to the 3. That's 528 times 10 to the 3 kilograms. Let's figure out the velocity of this structure together, and then we'll figure out the impulse that the ISS applied to the shuttle. So that'll be our end goal. What is the impulse? Impulse ISS on shuttle. So first, this velocity. We need to figure out the momentum in this system, which is given by P equals mv, so 78 times 10 to the 3 times 10, plus the momentum of this object. Of course it's 0 since velocity is 0. So momentum is 780 times 10 to the 3 kilograms times meters per second. Since momentum in a system is conserved, the momentum over here is also going to be 780 times 10 to the 3. And we know that must be made up of the mass of this object, which is 528 times 10 to the 3, multiplied by this velocity. So if I take P and divide by m, I can find the velocity, and that's 780 times 10 to the 3 divided by 528 times 10 to the 3, and that comes to, where is this, 1.47 meters per second. So velocity equals 1.47 meters per second. Now, the impulse of the ISS on the shuttle. The impulse is made up of the change of momentum on the shuttle. If the impulse is being applied to the shuttle, it must give a change in momentum of the shuttle. So we'll figure that out, which equals Pf, take Pi, Now, we know pi. It was 780 times 10 to the 3. But PF is a little bit trickier. PF is given over here. When we look at the shuttle in isolation, 78 times 10 to the 3, P is given by MV, which is 78 times 10 to the 3, multiplied by 1.47, because this whole connected system is moving at the same rate. So we can plug that in over here. That's 70. Ooh. Yes, that's the PF is 78 times 10 to the 3 times 1.47. And if you plug this into your calculator, it should come out with negative 6.6 times 10 to the 5 newtons seconds. That is the impulse. The reason it came out as negative is because the force is being applied to the left, and we've already set our positive direction as that direction there. So that is the impulse of the ISS on the shuttle, and the bonus question is, what is the impulse of the shuttle on the ISS? And we could do the working out. In fact, I think we will. It's getting a little crowded, but I'll move everything over. Actually, can I scale things? Let's have a look. Scale. There we go. Move it over here. The impulse of the shuttle on the ISS is equal to the change in momentum of the ISS. Which is equal to the final momentum of the ISS, take away the initial momentum of the ISS, which equals, what was the mass of the ISS? 450. 450 times 10 to the 3 multiplied by 1.47, and the initial momentum was 0. So if I get my calculator out, I know what this should come out as. I'm hoping it will come out as. So that's one of the problems of using your phone as a calculator. It tends to go off in the middle of these things. Yep. That's 6.6 times 10 to the 5 Newton seconds, which is the equal in magnitude but opposite to the impulse applied on the shuttle. So as in the question before, the impulse of one object on another is matched by that other object on the first object, thereby conserving momentum.